Okay, so good afternoon, everyone. Thank you very much for having me here. So today I'm going to talk about how to connect brains with machines and what's the principle and the challenge, and is it possible like to increase the multitasking ability or to increase the cognitive abilities for human in the future, not only for handicapped people but also for healthy people to be able to do many tasks at the same time. So I think most of you know Elon Musk, who created this new startup Neuralink, and we are not sure if this new chips will make you more smarter than Elon Musk. I'm sure that both of you, all of you here, I'm sure that you are very smart. I'm sure about your IQ. But what we want to do is to give a human a possibility to not only be able to control machines by his or her brain, but also to maybe share information or maybe to create like a brain network between each one here, and we can maybe solve complex problem. But before arriving to that stage, we would like to know what is BCI, what is possible and what is not possible at this stage. So brain-computer interface is a system that can do many things, but the most important is to replace, restore, enhance, supplement, or improve the CNS output, so thereby change the ongoing interaction between the CNS and the external or internal environment. So most of people have maybe spinal cord injury problem, or they have some stroke on their brain, so they will not be able to communicate with their environment. So BCI, or brain-computer interface, can give them the possibility to do many things. So this is just a brief history about BCI. So the first one who record human EEG or brain activity was Hans Berger, and we are sorry that he commits suicide. So in 1970, like the first term of like BCI, brain-computer interface, was appeared in the literature from University of California, Los Angeles. And then I think until 1988, the first people who published a paper who could control mobile robot using EEG, using brain activity. It was in 1988. And I'm sure that most of you know one of these 2 or 3 movies or series. So I think it was from a past, like a human would like to control things using his or her brain, because I think it's the natural way to interact with the machines. It's much better than using the voice or using our hand, or maybe to use muscles activity or any other way of communication. I think controlling things with our brain, like turn off or turn on the light, will be more interesting in the future. So if any one of you would like to develop his or her own BCI, it's very easy. You can just collect your brain activity using whatever you want, like invasive or non-invasive measurement. If you go for invasive, you need to do surgery. You need to put the electrode on the brain directly, so you will get high resolution. But maybe in the temporal aspect. But if we talk about, you cannot measure the whole brain if you use the ECG or ECOG, where the electrodes are on the brain directly. But if we use EEG or MEG, the electroencephalography, where it's non-invasive technique, so we can measure the whole brain, but we will lose maybe some resolution in the temporal aspect. So when you collect your data, your EEG, but before, even collecting your data, you need experimental paradigm. So we cannot collect data just like that, like in a public space or something. So we need to propose an experimental paradigm, and then we ask the subject maybe to follow some instruction, and then we start recording this information from the user, and we will see some relevant pattern or features, and we will try to extract this relevant pattern from the brain. We will check the brain activation maybe in the both hemispheres, and we will try to see which brain area is more responsive. And then we propose we can use whatever, like deep learning or supervector machine, any decoding algorithm or classification methods. And then we convert this result, this decoder result, to a command where we can control, for example, robotic arm, wheelchair, or robotic suit, or even control drone or a Star Wars robot, for example. We can even write if we would like to do that. So, but to do this, we as I said, we need experimental paradigm. So we need some neuroscience aspect. The first one, we call it P300 BCI speller. So where it's very common in developing brain-computer interface. So you can imagine that if we want to check if someone is lying or not, so we can show him some pictures, and the moment he will see someone that he recognizes him, even if he lie, his brain will generate this P300, which is positive wave that appears 300 milliseconds after stimuli, visual stimuli, tactile stimuli, or even auditory stimuli. So based on this neuroscientific characteristic in the brain, we can use it for controlling or for writing or for whatever we want. So you can imagine that you have here matrix, so we will flash the row and the column randomly, and at the time where you see the letter that you want to write flashing, so at that time your brain will generate this P300. So, and we will collect it, and then we will develop an algorithm that will be able to decode at what time you really generate this P300, and by that we can recognize the letter that you want to write. The second principle, we call it SSVEP, or steady state visual evoked potential. This is a little bit looks like P300, but it's completely different. So here we have, you can imagine that we, instead of flashing the row and the column, we flash each character with different frequency. So when you flash each icon, for example, with different frequency, your brain will synchronize, will generate the same frequency. So based on this, we can use just Fourier transform, FFT, or fast Fourier transform to find which frequency you are looking at. And based on that, we can translate it to commands to the robot to go left or right or up or down. So this is, we call it SSVP. We can use this technology to control robot, to control wheelchair, whatever we want. And we can go to 12 or maybe more than that. So not only 4 icons, we can go to 12 or maybe 15 icons. But it's limited. I mean, no more than 12 maybe. The last one, it's a little bit different from the SSVEP and P300, because the SSVEP and P300, both of them need synchronization between the user and the screen. So to generate P300 from your brain or SSVEP, you need to look at the screen. But motor imagery is different. Motor imagery based BCI is different because you just close your eyes and you just imagine that you are moving your left hand or your right hand, and we can see some characteristic on your left or right hemispheres. So this one also, we check on the signal, we check some frequencies. We know this characteristic very well, and based on that, you can control whatever you want. For example, if you are imagining, because the most interesting in your brain that when you imagine moving your hand or you perform the movement, it's almost same characteristic because you are using the sensory motor area, so the motor area will generate the same characteristic. Of course, the somatosensory will not generate the same characteristic, but the mainly one is the motor area. So we use this characteristic to distinguish between, for example, if you are moving your right hand or left hand. And we know also that if you are moving your right hand, so your left hemispheres will be activated and vice versa. So based on that, we can control wheelchair or whatever we want. So, but the most important thing we have to know that we can, let's say between brackets, we can read your brain activity and we can also write brain activity, which means we can record your brain activity using non-invasive or invasive techniques such as ECOG or ECOG, fMRI, MEG, EEG. So here we can measure what your brain is telling us. So we can measure your brain activity. So, and then we can use it to control any machine. But at the same time, let's say between brackets, we can write or we can send some signal to your brain using TMS technique or even optogenetics or sonogenetics. Optogenetics, we send some light, or sonogenetics, we send some sound. So, or we can send electrical current. So we use this technique. They are very, very useful techniques. So you can imagine that if someone has Parkinson's disease or someone, for example, he's suffering from depression or something, we can send some signal to the area responsible about depression, for example. We can make him happy, or it's very useful because in the future you can imagine that some people, they have maybe they have some bad experience in their life, so they keep having nightmare every day. So imagine if we will be able to remove this memory from their brain, so it will be great for them. So you can see that we can read brain activity and at the same time we can, between brackets, write the brain activity. So brain-computer interface, it's very useful. So you can see that we can even go for brain-to-brain interface. I will talk about that in the upcoming slide. So it's brain-computer interface and computer-brain interface. So when you send the signal to your brain, and you can see a video on YouTube, someone who has like Parkinson's disease, they are always shaking. So when just by sending some signal to their brain, they will stop shaking. So it's very, very useful technology. Is it ethical, not ethical? I think if it's very useful for us, I'm computer scientists, so we do believe that if the technology is very useful for us, so we don't care if it's ethical or not. This is not our job. So we will let like philosopher or government decide about that. So the brain-computer interface is very helpful not only for handicapped people, but also for old citizens. Like you can imagine that even I do believe that aging, it's a disease. It's not something natural. So we do believe that in the future, we can live better life if we can integrate brain-computer interface in our daily life. So we can control a smart home. We can even like have robotic suit, so we can be more stronger. So, or we can just control a wheelchair, so we can be more independent. It's very important. So the technology can make us more independent. So that's why we really love this technology. Okay, so we can develop non-clinical application and clinical application. So you can imagine like non-clinical application, we can use this technology for meditation, for playing with a robot, for controlling drone, or just playing video games. We can even share this information between two people who can play one video game. So it will be more cooperative and collaborative. And also this technology is most likely designed for handicapped people. So we can even restore the vision, we can restore the hearing. Of course, you will not be able to see us with high resolution, but it's much better than nothing. And also you can restore even the movement, the sensation. You can see this paper was these two videos or these two pictures, these two work have been published on Nature. So one, I think 2012, the other one is 2016. So they are very, very breakthrough in BCI, where we could like restore this paralyzed hand. So instead of just controlling a robotic arm, no, we can even restore your paralyzed hand. So that's something very important. And maybe some crazy application for BCI where you can control another human hand. This is brain-to-brain interface, where this guy was wearing the EEG, non-invasive technology. The other one was putting the TMS on his head so he could control his finger. So that's brain-to-brain interface. So someone, maybe he will ask, why should we control my friend's hand? We do believe that it's very important to develop this brain-to-brain interface because there is many complicated problem in this world. So instead of bring one scientist and ask him to solve very complex problem, that will be difficult. We can bring 5 and connect their brain, create this brain network, and they will work together to solve one problem. So that will be more faster and maybe more efficient. And also some Japanese researchers, they could even start reading the dream so they can see what you are dreaming. Is it ethical? It's not ethical. We don't care about that. So you can ask your wife. I mean, she will love to read your brain, so she can know everything about you. And also some Chinese, they could control cockroach. So that's also very interesting. So instead of wasting time developing robots and it's huge money, so instead of that, we can just control some existing animals and we can do a lot of things. Is it ethical or not ethical? It's not me to decide. I think this is the society and the government can decide. And also maybe this is still just a joke, but maybe in the future, instead of having too much wolf at home, why not just talking with your dog? I think it's much better. It's more, I think, interesting. So I will talk now about some realistic BCI, where when I was in Tokyo Institute of Technology, I could control video games using just 2 electrodes around the ear. So this is very, very useful and very, very powerful technology. So imagine instead of using the whole cup, I just use 2 electrodes around the ear. So instead of using also some electrode around the eye, so we call it EOG. So it's not good. It's not good for even the beauty. So we put just 2 electrodes and we could control using very simple algorithm without even, very short time for calibration, and it was very successful. And in 2019, we used the same technology to control video games with 2 characters. So imagine here 2 people were sitting, and this one is controlling 1 character, and the other one is controlling the second character. So one of them is using his hand, but the second one he's using only his brain activity. So you can see. So we record in this video, we record the eye movement from the EEG instead of recording the eye movement from the EOG. Okay. So this is. So we even wrote a patent about this. So we think about developing this hardware. We already start developing this hardware. So imagine just small devices where we can collect your brain activity and your eye movement, and we can even get some information if you are tired, if you are lazy, if you want to sleep or something. So this is very important. Even the concentration, so a student can use it and many other people. And this is another work, I think it was in 2018, where I participated with my Japanese student and we won the first place. This was in IEEE SMC in Japan, Miyazaki. So there is a hackathon, it's very well-known hackathon, in brain-computer interface hackathon. So we participated. What we did, we developed video games, we call it Brainio. So it's like Mario. So where someone could help another person. You can imagine we have 2 people here. So this person is trying to avoid some obstacle. He cannot move from this place to another place. So we need to remove, for example, this obstacle. So the other one, using his brain, he has some colors there, so he can remove whatever his friend or her friend wants. And also I participated with my student to another hackathon in 2019 in Italy, in Bali, and they won the 3rd place, where they could control a drone. And here what they did, they tried to they control this drone using their brain, but the idea was to chase another drone using only your brain. So, and they won the third place. So the idea is, imagine that, I told you, we don't care too much about ethical. So imagine if you are in the war, we do believe that, we do believe that soldiers need more assistance, or like something like we need mobile robot, we need like drone, we need many things. So imagine in the future, so you are wearing this EEG cap and you are controlling the drone, you are receiving in your Google Glass, you are receiving information, you are getting all of this, and you can chase just using your brain. Why? Because we do believe that your hands are busy, you are doing another thing. So this is what we call like multitask. So we would like to increase this multitask ability. So this is the principle, how it works is just like you have P300 speller, you have different icons, and then when any one of them flash, so you just concentrate, your brain will generate this P300 wave, and then we can collect it using decoding algorithm, and we can send it to the drone, and the drone will move wherever you want. So you can see all the icons. We have here 12 icons. We can go for more than that. And also we can also combine brain activity and non-brain activity. So instead of using only brain activity, we can combine your eye movement with the brain activity, or your muscles activity with your brain activity, to get more or high performance or high accuracy, or even increase the dimensionality. So the number of commands or degree of freedom will be increased. So you can see here also we try to use this robotic arm for write something like hi or something, and all of this work have been published. This is maybe the most interesting work. I really love it. I did it with at Osaka University with Hiroshi Ishiguro, and the paper was in the cover page of IEEE Transaction Neural System and Rehabilitation Engineering. I did it in 2018. So here it's very funny, you know, it's the problems in Japan are a little bit different from the problem here. So these people, you know, they work hard, they don't have time, and even young people, they have to spend more time at office, and you know, when they spend too much time over time or over time, so they don't become, you know, efficient. Their social life will not be good. You know, they don't have like work-life balance, and most of them, they got stressed, or they even do karoshi, which is they die, you know, from working too much. So to find a solution for these people to keep the same productivity, we don't want to decrease the productivity, but we want to increase the time. We want to increase the time they spend at the office. So what we think, we do believe that our brain is able to control more than two hands. So we can add a third arm, a robotic arm, so they can have multitask. So that's what we do believe. We do believe that multitask can give you less time, less energy, and maybe maximize the productivity. Maybe someone asks, is it realistic? Yes, there is some 1% people or 2% people in the world, they already have this ability. So we just want to give it free for everyone. That's the objective of this study. So you can imagine that in the future, if you have the third arm, it's not only for controlling, it's for sensation, for many things. So, and there is a paper about this. So it's very, very interesting. You can understand that this information overload, so we can use it. We can benefit from this information and give a brain more arms or more capacity. So this is possible. Until today, most of people, they have been trying to do that, but they use some mechanical aspect, or they just use some muscles activity. They didn't use brain activity. We do believe that controlling things using brain activity is the most natural way. So that's why we start our experiment with Professor Hiroshi Ishiguro. So we want to control his Geminoid. Geminoid is just a human-like robot. So also Professor Hiroshi Ishiguro believed that between brackets we are just a biological machine. So we don't have definition of human, of course. Like I'm talking scientifically speaking, we don't have clear definition of what is a human. But imagine in the future if we can create a biological, not a biological machine, we can create like artificial machine that behave same like a human. At that time, we will have a clear definition for a human. Maybe we will be more sure that there is no soul, maybe. So this is just an idea. So what we want to do before controlling the third arm, at that moment, people, they could only control unilateral hand. So what I was trying to do is to control bilateral hand. For example, moving your both hands or moving like opening this one and closing this one at the same time. So of course, and then we try to do it in real time to control the Geminoid. So of course, as I said, to develop brain-computer interface, the most important thing is to propose your experimental paradigm. So we propose our experimental paradigm, and all of this time are very, very important. For example, this 3 seconds, it's not just like this, and this 0.5, and even why we put the instruction here, we didn't put them. So we asked the subject to execute the movement here and not here, just to avoid the visual like imagination, because here we ask him to imagine the movement. So imagine that if we ask him to imagine the movement here, so we will not have what we need, like kinematic imagination. We will have visual imagination. So we did this experiment for maybe 20 subjects using MEG. So this is very expensive and not portable devices, but it will give us more high resolution. It's very, very important, high resolution in the spatial and temporal area. So, So what we did here, we just asked him to perform the movement and imagine the movement at the same time. So we record mini sessions, and then we try to analyze this brain activity. So what we got that, this is very, very typical brain waves. So imagine that when you close your hand, we will see here decreasing, energy decreasing or power decreasing in the alpha and beta bands, the beta and alpha band. And then this decreasing, it will be here beta rebound after 0.5, and we will see also high gamma band. So this is, we have some frequency bands in your brain. But the most important that even before closing your hand, your brain will plan to close your hand without even you notice that you want to close your hand. So even before you start closing your hand, we can see some decrease in here, but it was difficult to use it for decode the movement, so we just use this 0.5. So if we use this one, the classification accuracy would be very nice, but we cannot because it's 1 second, it's too much. So we want to decode the information between 0 second and 0.5. And you can see that we did this one for the whole sensors, because we are using here MEG, we are not using EEG, so it's not electrode, they are sensors. So we check the whole sensors, around more than 300 sensors, and we got almost the same characteristic, but depend on the movement, if it's like bilateral closing or opening and so on. And we also did some statistical analysis to check which sensors contribute more in this activity. And based on this, we check for the real movement and imagined movement, and we check all the sensors, and we try to find some characteristics that can distinguish between bilateral movement. And it was, I think, the first paper using MEG for decoding bilateral movement. So you can see here, I hope you can see the video very clear. So the human-like robot was This looks like Professor Hiroshi Ishiguro was at ATR in Kyoto. And this one was in Osaka. So you can see the MEG room here. I was the one who was recording this movement. So this person or this lady was like imagining and performing the movement, okay? She has some instruction here, and we will send the result to the robot. So if you see here, you will see the robot close his hand. You can focus here. Maybe he will close this one or open it. Yes, he closed this one based on the lady in the room. So we did the bilateral movement, but don't forget that our goal was not to stop in the bilateral movement, but was to go for the third arm, okay? And this one was the co-authors of the paper, if you remember, the one I just showed you. So at the same time, they were working on another project, but using EEG. To be honest, for people, neuroscientist people, they do believe that when you use EEG, you have a lot of artifacts. So it's not accurate. It's not, we don't really believe the result. I mean, we don't believe it's coming from the brain. Maybe it's coming from some artifact, muscles artifact. So yes, they could control the robotic arm, but that's why we propose we proposed almost the same experiment here. I hope you can see it, but using MEG. I told you, using MEG is the best. So we asked this subject to play here. There is a ball here, and at the same time, he's moving both hands, and there is the third arm here. We ask him to think, to close, to grasp that bottle, and we recorded this data for 20 subjects, and we are still analyzing this data, so the result is not coming yet. So that's why we do believe that using MEG will give you more accurate result about brain activity, not just muscles activity or any other artifact. So in the end, we do believe that in the future, maybe we will have the chance to connect our brain to internet, so we will be almost same, you know. So maybe some students will have the same skills like professors, I'm not sure about that. And also we will have some problems, maybe some brain hacking, or we can control each one because we will have the chance, maybe some virus will go to your brain, we are not sure about that. And brain-to-brain interface, as I said, there is a project and people, they really start working on this, so they could, you know, they could make network between 2-3 brains, and they published this one in Nature. So it's useful, it's now, and transfer memories and maybe download the new skills in the future, maybe even get a new body. You know, we do believe that our brain has more capacity than we are weak. We don't like our body. We need something strong. We need something more useful. I do believe that biological machines are not the best, maybe evolution, I'm not sure, so maybe we need more things. And also maybe we can live outside our body, so to have some experience about paradise, and instead of waiting for the paradise maybe a long time. So we can do that. Thank you very much.